here in our screens. Okay, so welcome back to the final talk on our Tuesday afternoon session in our 5th workshop on fluids and PDEs. Our speaker now is Trevor Leslie from the University of Southern California. We will speak about sticky particle methods for the 1D Euler alignment system. Thank you very much, Trevor, for giving a talk in our conference. You can start anytime you want.
Thanks very much. Hi, everyone. Thank you for coming, and thanks to the organizers for the invitation to speak, and thank you for the introduction as well. Today I'll be talking about the 1D Euler alignment system. I'll describe a couple of projects that I've worked on relating to this system, but the thing that I want to focus on is some recent joint work with Changhui Tan. We put a paper on the archive about a month ago on weak solutions of the Euler alignment system using sticky particle methods originally developed for the pressureless Euler equations. All right, so let me first tell you what the equations are that we're dealing with. I've written down here the Cucker-Smale system of ODEs, which describe the motion of n agents with masses, positions, and velocities, mi, xi, and vi respectively, subject to a communication protocol phi. Each term on the right-hand side of the momentum equation here tries to bring the velocity of agent I a little bit closer to the agent to that of agent J, and how hard it tries to do this depends on both the mass of agent J and on how much communication there is between agent I and J, and that's encoded in this communication protocol. The Euler alignment system, which is the primary object of study in this talk, is basically a hydrodynamic version of the Cucker-Smale system. For a large class of communication protocols, phi, one can rigorously go from the Cucker-Smale system to a kinetic version, which I didn't write here, to the Euler alignment system that is written here. So the Cucker-Smale and Euler alignment systems fall under the umbrella of a field called collective dynamics or collective behavior. And the question one wants to answer here is how large-scale structures can emerge from small-scale interactions in biological systems or otherwise. The prototypical example one often brings up is a flock of birds. There have been field studies done on flocks of starlings, for example, that have concluded that these birds really only pay attention to their 6 or 7 nearest neighbors. In light of the sort of local interaction of these, the local nature of these interactions, it's pretty remarkable that they can form such a large cohesive group of sometimes thousands of birds. And we'd like to better understand the mechanism behind this phenomenon. So we can't hope to capture all the intricacies of for example, a biological system like a flock of birds with a differential equation as simple as Cucker-Smale or Euler alignment. But this system is significant because despite its simplicity, it still captures some of the important features that we'd like to understand, and so functions effectively as sort of a minimum model for alignment dynamics. Mathematically, we say that flocking occurs if the diameter of the agents or the density profile remains uniformly bounded in time so that the agents move in a cohesive group. And we say that velocity alignment occurs if the diameter of the velocities tends to 0 in the time asymptotic limit. These concepts are most obviously relevant for biological systems, but they also have technological applications, for example, satellite navigation. These applications are certainly interesting, but the viewpoint that I'll take in this talk is a little bit more abstract. Our goal today will be to study the consequences of the non-local alignment forcing in isolation. Okay, so we want to study the non-local alignment forcing, but let's remember that this force is being added to the pressureless Euler equations, which is what we get if we set the communication protocol equal to 0. So I think it's natural to take the pressureless Euler system as our baseline and see what we can learn from it. And I'll talk about dimension 1 almost exclusively here. To get started, let's define the function c to be u, the velocity, plus capital phi convolved with the density. Here, capital phi is the odd antiderivative of the communication protocol little phi. Of course, if there's no communication, then u and psi are just the same function. But in any case, this function psi allows us to write the 1D Euler alignment system in a form very similar to the 1D pressureless Euler system. The difference is that in this second equation that you see here, one replaces one factor of u in the pressureless Euler system with psi in the Euler alignment system. With all this in mind, I think it's reasonable to surmise that a sensible first step to take to try to understand the 1D Euler alignment system is to try to understand the role of psi. Basically, we want to know to what extent it plays the role of u, and to what extent it facilitates outcomes beyond what the pressureless Euler system can produce. If you look at the Lagrangian trajectories for the pressureless Euler system, you'll see that they're all straight line paths. The velocity is constant along each characteristic path, and these trajectories either separate linearly, run parallel for all time, or cross in finite time. And this last possibility occurs if and only if the velocity u naught decreases somewhere as you move from left to right. For the Euler alignment system, the alignment forcing bends the trajectories to allow for some more interesting possibilities. Certainly, trajectories can separate linearly or cross in finite time, but they need not start out with parallel velocities in order for their mutual separation distance to converge to a constant in a long time limit. In terms of well-posedness, the most significant question is whether or not trajectories actually cross. And one can show that trajectories cross if and only if psi naught, rather than u naught, as was the case for pressureless Euler, decreases somewhere as you move from left to right. You can see this by using the fact that psi is transported along characteristics. So we get a global and time smooth solution from regular data if and only if psi naught is non-decreasing in the support of the density profile. And this observation is a version of the so-called critical threshold condition for the 1D Euler alignment system, which originally appeared in a 2016 paper of Carrillo, Choi, Tadmore, and Tan. But the formulation on this slide is from a paper of mine from last year. Basically, the added value from this later paper is the analysis of the Lagrangian trajectories, which gives a really transparent way to understand the situation, and also the removal of the dependence on non-physical vacuum velocity, which is something that was sort of embedded in this, this earlier work. So let me put into context the two papers that I just mentioned by providing a list, admittedly a pretty biased one, of some literature on the Euler alignment system with smooth protocols. Again, this is by no means a complete list. It's just a list of the papers that happen to be most relevant for my talk. One thing I want to point out is that there's not much known about well-posedness in higher dimensions. There's this paper by Hay and Tadmore from 2017, which has some partial results. And last year, Lear and Schvidquay looked at the case of unidirectional solutions, where the velocity points in a single direction for all time. They also looked at perturbations of this scenario. Later, Daniel, Roman, Aiton, and I sort of joined forces last year to refine the Lagrangian analysis of this paper and to put it in the unidirectional setting of this one. In particular, we paid special attention to the case where two trajectories remain separated for all finite time, but meet at time infinity. This scenario creates a time asymptotic concentration of mass. These trajectories that meet at time infinity, they trap all the mass that started between them, and when they meet at a point, all that mass gets crushed to that point. And this is sort of a borderline case between global well-posedness on one hand and finite time blowup on the other hand for smooth solutions. Finally, the headline result of my talk is my recent paper with Chang-Hui Tan, where we looked at what can happen beyond the blowup time by providing a theory of weak solutions. So this paper is the first systematic treatment of weak solutions for the Euler alignment system with general smooth protocol phi. But I should mention that there have been 3 other papers that deal with weak solution in the special case where phi is identically equal to 1. These are certainly important works, but they don't shed too much light on what to do in the more general setup, because the special form of this communication protocol causes the non-locality, which is sort of the main difficulty, to completely drop out of the equation. So I won't talk more about these, but I do want to mention that they're there. Okay, so I'm going to talk about weak solutions in just a moment, but before I go there, I do want to spend just 1 minute talking about this borderline case where we treated mass concentration. So as I already mentioned, we've got trajectories that start out, that meet at time infinity, and they crush all the mass in between them to a point. For smooth solutions with slowly decaying communication protocols, we can actually say exactly when this happens. It occurs when the function C0 is constant on an interval, or equivalently when the derivative E0 is 0. And this occurs, basically, this is a formulation of that statement. The difference between C0 controls the long time distance between trajectories. And so if the right-hand side of this comparison is 0, then so is the left-hand side. If we look at unidirectional solutions, we can actually see mass concentration sets that look like our favorite union of curves. On the left-hand side here, we have our choice of the 0 set of the function E0. And on the right, we have the corresponding set at time plus infinity where the mass concentrates. The figures on the right-hand side are just sketches, but they're accurate up to a C1 diffeomorphism that preserves the horizontal slices. If we're more careful with our analysis, we can even cook up explicit initial data in the 1D case, such that the mass concentrates at time plus infinity onto a set of our favorite Hausdorff dimension between 0 and 1. And I think this is really interesting. But anyway, all of this is for a different talk, and I have to move on now if I want to say anything meaningful about the case of weak solutions. Smooth solutions remain regular if the trajectories remain separated. If they meet at time infinity, we get mass concentration. But what if they actually meet in finite time? How do we continue the solution beyond that time? Clearly, we need some notion of weak solution. The equations, as we've been writing them down, already appear in divergence form, so it's pretty trivial to formulate a sensible notion of weak solution here. But the most naive version of a weak solution won't get you uniqueness. And this is a problem that already appears for the pressureless Euler equations. Basically, if you take 2-point masses moving along straight line paths and colliding at time t equals 0, you can specify a range of different post-collisional velocities. These particles can just keep minding their own business and not interact at all, or we can have completely elastic or completely inelastic collisions or something in between. And all of these options will solve the weak form of the pressureless Euler system. So we need some additional criterion to single out a distinguished weak solution. Now, if you're only interested in the discrete setup of the previous slide, you might be able to convince yourself pretty quickly that a good selection principle should correspond to completely inelastic collisions, or sticky particles, as the situation is called. This type of collision dissipates the most energy while still conserving momentum. One, of course, does have to formulate some independent selection criteria for non-discrete initial data. But it turns out that all the success stories of the pressureless Euler theory are compatible with this sticky particle model. So let's describe these sticky particle interactions a little bit more concretely. We've got capital N particles of masses mi, positions xi, and velocities vi, and they move in straight line paths except when they collide. And when they collide, they stick together, meaning that this set j sub I of t, which encodes the set of indices j which are stuck to agent I, This set can't shed particles. It can only get larger. And the other criterion is we need collisions to conserve momentum. Just some conventions. I'll always set the total mass equal to 1 and take the particles to be indexed in increasing order from left to right. There are two approaches to studying the pressureless Euler system, which by now are basically considered classical. First, there's a variational approach, which has its origins in the paper of Rykov and Sinai from '96. And I'm leaving out a few papers in between these two. But the big success story in terms of uniqueness for the variational method is this paper of Huang and Wang from 2001. They construct a solution by a method they refer to as the generalized potential, though the construction is essentially equivalent to Rykov and Sinai's. And more importantly, they show that this inequality serves as an entropy condition strong enough to guarantee uniqueness. And this is a very nice result, and we'd love to say something similar for the Euler alignment system, but it's not clear yet, at least to me, whether this framework can be applied successfully. The other approach was pioneered by Brenier and Grenier from '98. Their paper contains several new ideas, probably the most important of which is that the dynamics of the pressureless Euler system can be captured in a single scalar conservation law. The unique entropy condition of this scalar conservation law then serves as a selection principle for the system. This idea has been extended and refined in several directions. One particularly significant extension is due to Nguyen and Tudorascu, who used the method to treat the Euler-Poisson system. And our approach is largely inspired by Brenier and Grenier's work. Actually, the skeleton of the argument that Changhui and I use for the Euler alignment system is very reminiscent of Brenier and Grenier's paper. Let me point out the two main features. First of all, if you refer to this diagram, in blue, we have the outline of what Changhui and I are calling the entropic selection principle. This idea, again, is already present in Brenier and Grenier's paper, but they didn't really call it this. So what this is we want to encode the 1D Euler alignment system in not a scalar conservation law in this case, but a scalar balance law. And we use the corresponding entropy condition for the balance law as a selection principle for our original system. So we take our initial data, we translate it into a cumulative mass distribution, M0, and flux for the scalar balance law. We generate the entropy solution for the balance law. And finally, we translate back to the velocity, density, momentum. The other main feature here is outlined in red. In order to actually generate the solution that connects these two blue boxes at the M level, we discretize. And amazingly, we can find that the entropy solutions of these of the discretized M equations can be generated by running the sticky particle Cucker-Smale dynamics. This serves as a front tracking approximation for the M equation. What I mean by sticky particle Cucker-Smale is it is what it sounds like. We run the sticky particle, we run the Cucker-Smale dynamics until particles collide, and when they collide, we insist on completely inelastic collisions. So we can formally derive the scalar balance law that encodes the 1D Euler alignment system by integrating the equations for rho and for rho psi. Then we want to choose a function a such that q is equal to a composed of m at time 0. And if everything is smooth, this implies that q and a of m are identical because they satisfy the same transport equation with the same initial data. This choice of a turns out to serve as a flux for our new scalar balance law. If we compute partial t of m plus partial x of a composed of m, this gives us this right-hand side here, and now our scalar balance law. This is again just a formal derivation, but we can make it rigorous. A couple of notes here. First of all, our flux is not the momentum, which already sets our framework apart from Brenier and Grenier's, as well as from the works on Euler-Poisson that have used this setup. Here, by the way, is another instance where C replaces the role typically played by U in our setup. Another note, because this balance law isn't, at least to my knowledge, in a form that's treated in the literature, we do need to build a well-posedness theory for this equation by hand. And this is mostly not a big deal, but one big challenge of the analysis is the fact that the alignment forcing is partially buried in this flux term, and we need to reunite it with the other part of the alignment forcing in order to take advantage of some cancellations. When we do that, though, we are able to achieve the same stability bound with respect to the initial data and the flux that one has for scalar conservation laws, which is pretty nice. So let me say just a few more words about the sticky particle Cucker-Smale dynamics and how we use them, in particular how we use them in relation to the AM equation. One interesting thing about sticky particle Cucker-Smale, and something that I've sort of already previewed at the hydrodynamic level, is that even though the particles don't move in straight lines, we do have a quantity that's constant along trajectories, except at collision times, of course. This quantity is Ci, and this is the discrete analog of the function C that we talked a lot about earlier. In fact, the quantities Ci essentially take the place of the VIs from the original sticky particle dynamics, except that they don't, of course, represent the velocities. For one thing, we have conservation of the C momentum, if you will. Next, it's the monotonicity of the Psi's, not the Vi's, that determines whether or not particles can actually catch up to each other and collide. And finally, we have this barycentric lemma for the Psi's, which basically says that prior to a collision, the average Psi in the left group of particles exceeds the average Psi on the right. And it turns out that this property, conservation of Psi momentum, guarantees the Rankine-Huguenot condition, holds for the corresponding solution of the M equation, while this property gives us the Olenek condition. Okay, so I'm close to out of time, and I don't have time to give any proofs, but let me quickly summarize what it is that Changhui and I have actually managed to prove. First of all, we showed the existence of a distinguished weak solution for initial data consisting of a compactly supported probability measure, rho naught, and a velocity, u naught, which is L infinity with respect to d rho naught. Next, we proved that a certain Cucker-Smale approximation scheme converges to our solution in Wasserstein 1. And we showed that that we have a rate for this convergence if we have some regularity on the velocity field. Actually, this requires two slightly different approximation schemes. Anyway, and finally, we have the sort of expected flocking properties that we inherit from the discrete dynamics. We get flocking, we get velocity alignment, and we even get the existence of a limiting density measure under the same slow decay assumptions on phi that we needed before when we discussed mass concentration. Okay, so let me, I am out of time now, so let me not dwell on this slide. But I just want to mention that it's my hope that this entryway into weak solutions will generate some further activity in the area. And even just in the context of what we've talked about today, there are several really interesting directions to consider. One being the possible structure of this, this limiting density profile, which we understand in terms of mass concentration in the context of smooth solutions, but which is likely to be much more subtle for weak solutions. All right, that's all I have for now. Thanks very much.
Thank you very much, Trevor, for your very nice talk. By now, everybody should be able to unmute their microphones. Are there questions or comments for Trevor? Yes, Roman, please go ahead.
Yeah, so I think it's a very nice development in the sense that it gives us kind of a roadmap to study solutions with the entropy, negative entropy, right? The question is, okay, so this sticky particle model, you've done it for the smooth kernels, right?
Yes.
So what this reminds me another model which would behave in a very similar way, but for very, very singular communication kernel. So when the communication is equal to infinity on the ball of radius epsilon.
Mm-hmm.
So it will behave in exactly the same way, except that the particles don't have to actually collide. They have to approach the distance epsilon between each other. And then they get stuck and then they travel together. The exact exchange of momentum is actually not very clear, because it will, if three particles or more particles collide, it will actually depend at which angle they collide as well.
Sure,
so I was kind of wondering if if you can think of this sticky particle model as a limit of smooth communication models when the communication goes off to infinity on the ball of radius epsilon. It would be interesting to look at.
Yeah. I mean, it sounds like that would be a very potentially difficult direction to extend this, but a very interesting one. Yeah.
Yeah.
Are there more questions or comments for Trevor? If not, let's thank our speaker again for his very nice talk. Thank you very much, Trevor, for your talk today.
Thank you.
And with this talk, we finish our afternoon session and we finish our day this Tuesday in our workshop. So unless there are some announcements that the organizers want to make, I guess we should meet tomorrow morning Brazilian time. So thank you very much, all of you, for attending our talks and our poster session. And so then, see you tomorrow.